In this video, we're continuing section 1.3 on propositional equivalences, and we'll talk about how to use some common equivalences to show propositions are equivalent, or that they might be always true or always false. So I want to begin with a definition. We say that a proposition is a tautology if it is always true. So an example of that is if we have P or not P, because well, it's always going to be the case that one of them is going to be true. Like if P is true, not P is false, or if P was false, not P is true. But in either case, the or statement is going to be true. So P or not P is, we can write, it's equivalent to T. It is equivalent to a true statement. It's always true. It's a tautology. A proposition that is always false is called a contradiction. And an example of that is P and not P, because, well, if P is true, the other not P is false. And if P is false, not P is true. But there's no way that both of them are going to be true. And that's what I would need for the and statement to be true. So P and not P, that's false. They can't happen at the same time. And finally, a proposition that can be both of them, sometimes true, sometimes false, we call that a contingency. Okay, so what I want to do is this following example now. I want to show the proposition P and Q implies P implies Q, that this is a tautology using a chain of logical equivalences. So that means I want to do this without using a truth table. So we have already established the equivalence of some propositions in previous videos. So, for example, we've shown that P implies Q is equivalent to not P or Q. Sometimes we call this the implication law. Earlier in this video, we've shown that P or not P is true and P and not P is false. We've also shown these De Morgan's laws. There are other equivalences like this that are very quick to establish, like things like the commutative law, where if I have P or Q, that's equivalent to Q or P, which I think is kind of what we'd expect. So the idea with this is we're going to start with this proposition that we have, and when we use a chain of logical equivalences, instead of using a truth table to just show that it's always true at the end, I'm going to try to use these to show that I eventually get it's equal to or equivalent to a truth statement. Okay, so I'm going to start off with my proposition P implies Q implies P implies Q. So P and Q implies if P then Q. Okay, so how can I begin with this? Well, I notice that there's this implication here, P implies Q, and that reminds me of this implication law. So maybe I'll start with that. So this is going to be equivalent to P and Q implies, and then I'm going to use my implication law. So I'm going to write that. So we are going to be using implication here. And implication allows us to say that that is equivalent to not P or Q. Okay, so that worked very nicely for one of these implications, but I see another implication. So what if I tried the same thing? So if I tried the same thing with this next implication, it'll turn that implication into an or statement. And what I do is I do the negation of the first part. So the negation of P and Q. And then I get or the second statement, which is this whole thing. So or not P or Q. Okay, so far we've used implication twice. Implication to convert each of those implications into or statements. Okay, and one of the reasons why that's so nice is we have so many of these logical equivalences that involve or and statements, or negations. So next I notice we have a negation of this and statement, so I can use my De Morgan's law. And De Morgan's will turn this into the negation of P or the negation of Q, and then I still got my or, not P or Q. So this is by De Morgan's. De Morgan. Okay. So at this point, what we have is we have all or statements. Here's an or, here's an or, here's an or. Okay, so I like that. The other thing in terms of strategy that I'd like to be able to do is, I'm hoping to show that this is a tautology eventually. Eventually, I'm hoping to show that if I keep going, eventually that this will just be equivalent to a true statement. And there are two things here that I'd really like to get together, which are the not Q and the Q. I'd really like to get those together because I know that if we have Q or not Q, that's one of our tautologies. This is just true. So if we can somehow move those around to get them together, I can produce something that's just true. So how can I do that? Well, if I have just a bunch of or statements, I can use this associative property to reorder these parentheses. So this is going to be equivalent to, so right now I have a parentheses around these two things, and then I have or this whole thing. I can instead write that as not P, and then put a parentheses around this whole or statement. So I'll have or, and then that'll shift the parentheses to be around this. So I'll get my not Q, and then or this other stuff, not P or Q. Okay, so instead of my main parentheses being around this or statement, I'm shifting it to be around this or statement. That is just using the associative property. Associative. All right, so we are getting closer. Now I can switch the order. I can use my commutative law. We can use the commutative law to switch the spots of this Q and this not P. So that'll give me not P or, big parentheses, not Q or not P. And then close that big parentheses. Okay, so we are almost there at this point. What I want to do now is I want to give you an opportunity, quick, maybe 1 to 2 minutes, to see if you can keep going from here. Keep going from here, and eventually we're hoping, can we get this is eventually equal to just something that's true. Pause it in 4, 3, 2, 1, pause it and try it. See if we can keep this going from here. All right, so hopefully you did that. Hopefully you paused it and tried it. Let's talk about it together. Okay, so the next thing that I want to do to be able to get these together is, instead of having the parentheses around this or statement, let's use the associative property to move the parentheses around these things. So I'll get not P or, big parentheses, not Q or Q, and then or the not P now comes outside of the parentheses. So this is my associative law again. This is now my associative law. Okay, now this is great because my not Q or Q, I know that that is just a true statement. That is just true because this is going to come from this negation property. Okay, so this is equivalent to not P or, big parentheses, I get a true thing, or not P. So that's coming from negation. From negation. And now we are almost there. Now I have a true or something else. So true or something else, well, that comes from this, from domination. If I have a true thing or something else, well, the fact that this is true automatically makes the whole or statement true. So this whole thing just becomes true, and that is coming from that domination property. Domination. So this is equivalent to not P or a true statement. Then I can use the same idea. I have an or statement. One part is true. That's enough to guarantee the whole thing is true again by domination. By domination. And I finally got that this is equivalent to a true statement. Okay, so we have shown that the proposition that we started with is just equivalent to something that is true. Okay, so we've demonstrated that this is a tautology using what's called a chain of logical equivalences. Now, if we wanted to, we could have also done this using a truth table. We could have made a truth table for this whole thing, and we'd just be hoping to show that the last column ends up being all true. And that would work as well. In fact, for this example, just because this is not a super complicated proposition, that might even be quicker. But what I want to mention about this is using this method can be very useful when we have a whole lot of variables, so a whole lot of propositions. Like here, I just had P and Q as my variables, but sometimes we will have more. We might have 4 or 5 of these things. Because in general, when I have n variables, my truth table will have 2 to the n rows. Like we've seen that if there's a P and a Q, there's 2 choices for each, so we'll have 2 times 2, which is 4 rows. But if we had 3 of these things, like a P and a Q and a R, for each of them, it could be true or false, so we'd have 2 times 2 times 2, which would be 8 rows. So that's why if I had n of these variables, there'd be 2 to the n rows. So for example, if I had 5 of these propositions, of these variables, we'd have 2 to the 5, which is 32 rows. And that is a ton of rows to be putting in a truth table. That would make it very complicated. And in such a situation, using this approach, which might have seemed long in this example, but I was deliberately trying to do one that was a little bit more challenging. When there are more variables, then using this chain of logical equivalences can often be more efficient. Okay, so I want to just summarize now what are the ways that we have to show 2 propositions are equivalent. Well, the first way that we've seen is to use truth tables. We use truth tables and we try to show that the column for P and for Q at the end, whatever those outputs are, that they're the same. In this video, we've talked about how we can use this table of common equivalences, where you start off with one proposition, and you try to show that it's equivalent to the other proposition. So this table of common equivalences, you start off with whatever P is, you try to use these properties to eventually show that it's equivalent to whatever the other side is, to Q. The final way is we can try to show that P if and only if Q is a tautology. So 2 of these propositions are equivalent if P if and only if Q is a tautology. So for example, what would this have looked like in the problem that we just did? We would be trying to show not in the example that we just did. For example, say we wanted to show that the implication P implies Q is equivalent to not P or Q. Let's say I wanted to do this using this method. Well, then what I do is I make a truth table. I would have my P and my Q. Okay, we'd have all the other things that would finally build up to the left-hand side. That would build up to the left-hand side. The left-hand side, if and only if the right-hand side, if and only if not P or Q. So we want to set up and try to get the left-hand side if and only if the right-hand side. And we'd be hoping to show that these just end up being all true.